Hello everyone, you are welcome to this channel. Today I will be discussing another numerical method for solving differential equations. That is Runge Kutta of fourth order. In the earlier tutorial, I discussed the numerical method of Euler and improved Euler. So today we shall be looking at Runge Kutta. Runge Kutta is a very powerful numerical method which is more accurate than the Euler and the improved Euler. In using the Runge Kutta, we have four auxiliary quantities to quantify. We have the four auxiliary quantities to quantify: K1, K2, K3, and K4. So, to quantify them, K1 is equivalent to the Euler equation. The Euler. So, and K2 is as follows: xn plus half h and yn plus half k1. And the K3 is xm plus half h as well, and yn plus half k2. While the k4 is hf xm plus h and yn plus k3. So those are the four auxiliary quantities we have to quantify before we calculate our next y. So our next y is now yn 1 over 6 k1 plus k2 plus 2k3 plus k4. So let's see how to apply this procedure to our old example. So the example is to solve y prime is equal to x plus y, and our initial condition at x naught equals to 0, and our step size is given to be 0.2. So let's use the Runge Kutta method for this procedure. Just like before, we set up our table. As a student, you should set up your table as I'm doing. So xn, yn. Then try to create a column for calculation. Try to create a column for calculation. So it's always a good practice. So as given initially, at n is equal to 0, x naught is 0, and our y naught is 0. So the second step, we have our x to be 0.2, and our y is given by all of this. So how do we use this? We can do that as follows. So it means we calculate our K1 is equal to 0.2 xn plus yn. Our K2 equals to 0.2 xn plus half h, which is 0.1, plus yn plus what? Half k1, which is half k1. Then our k3 also is 0.2 xn plus 0.1, which is half h, plus yn plus half k2 in this case. Then our k4 rather is equals to 0.2 xn plus full h now, which will now be 0.2 plus yn plus full k3 plus full k3. So when we combine all those, we are going to arrive at something like this. It means our yn plus 1, which is equal to 1 over yn plus 1 over 6 stuff that I showed you earlier, yn plus 1 over 6. If we combine all of those terms and simplify, we are going to have something like this: 0.2214 xn plus yn plus 0.0214. So that is the term to compute our successive n. So for the when n is 1, when xn is 0.2, so we substitute the value for xn is 0. So that means our y1 is equal to 0.2214 0 plus 0 plus 0.0214. So that gives our y1 to be equal to what? To be equal to 0.0214. So that is going here, 0.0214. So let's compute for the other. So for other successive xn, we can see the values for their corresponding yn. So that is how to compute for Runge Kutta method. Please don't make mistakes. Some people do make mistake of trying to create a column for yn plus 1. It's not necessary, and it's even confusing. This same yn is the same as yn plus 1, because at here is y0. When it get to here, it means y0 plus 1. When it got to here, it means y1 plus 1, making y2. When it get to y3, it means y2 plus 1, making y3, and so on. So you don't need to create a column for the yn plus 1 column or the yn plus 1 term. So because it shows in the formula, does not mean you should create a column for it. The successful stage of y is yn plus 1. So under the same column of yn. So please get that correctly. So that is that on that. Please practice and master the procedure. And if you have any comment, please state it in the section below, and ensure you subscribe to the channel by clicking the button below. Thank you.